Okay, now that we've talked about what a subset is, what a proper subset is, and what it takes to be equal to sets, the next logical step is to talk about the size of a set. So we'll come up with this definition. We'll say let S be a set if there are exactly n distinct elements in S. Notice that is distinct elements in set S, where n is a non-negative integer. We say that S is a finite set and n is the cardinality of S. The cardinality of S is denoted by what looks like absolute value signs around the set S. So straight vertical lines around set S. So let's go ahead and look at an example. We'll say let A be the subset of odd positive integers less than 10. This is a set we've been referencing a bunch. We'll say then the cardinality of set A is equal to 5. That would be the positive integers less than 10. 1, 3, 5, 7, and 9. Another example. Let S be the set of English letters then we'll say cardinality of S is equal to 26. Another example. We'll say the cardinality of the empty set write it as cardinality of the empty set is equal to 0. Why? We'll say because the empty set has no elements. All right. Then we'll say the definition another one here. We'll say a set is that's not good looking. A set is said to be infinite if it is not finite. And example, the set of integers is infinite. And our accountability is going to be, getting ahead of ourselves a little bit. The size of a set is going to be important to know whether or not that set is a finite set or that set is an infinite set. Well, on the topic of sets and size of sets, we need to talk about power sets. And that leads us to yet another definition. We'll say, given a set S, the power set of S is the set of all subsets of the set S. So this is the set of all subsets. All right, and we'll say the power set of S is denoted by this P with kind of the long thing coming out of the top of it there of S. And we'll do an example. Say, what is the power set of the set 0, 1, 2? So, power set of 0, 1, 2 is the set of all subsets of this set 0, 1, 2. So what's that going to look like? Well, that means it's going to be equal to the set. So we have to open it with curly braces there. Remember, all sets have two subsets, the set themselves and the empty set. So we start with the empty set, and then the set of the element 0 is one of them, set of the element 1 is one of them, set of the element 2 is one of them. And now we start our couplets. So we get set 0 and 1, and we get set 0 and 2. Remember, these are unordered, so order does not matter. Then we'll go set 1 and 2, and finally the set itself, 0, 1, and 2. And then we close out that whole set. Okay? And make sure to note, like we talked about before, the empty set and the set itself are subsets. So you don't want to forget those in the power set. Okay? Another example here, we'll say the empty set has exactly one subset. So the power set of empty set is the empty set. That's different from the set of the empty set. The set of the empty set has exactly two subsets. It has the empty set and the set itself, which is the set of the empty set. So the power set of the set of the empty set is equal to the set of the empty set as well as the set of the empty set. Okay? And then also want to note a characteristic of these power sets. Say if a set has n elements, then the power set has 2 to the n elements. Okay, and we'll actually prove this later on. This little trick can be very helpful, though, just to make sure that when you're listing out the power set that you are hitting all of the sets and you're not missing any. And that concludes this section.